in a few seconds.
Okay,
Right. We should be good to go, Nathan. Thank you for coming today. It's all yours.
thank you. So, good morning, everyone. Good evening, good afternoon. Today we're going to start our spatial analysis 101, and it's important that we start with the very basics, as said in the Gemini group meeting. Um, we're gonna go from like zero. So we're gonna understand how to download the software, is gonna understand what every number mean, and then we're gonna start building our knowledge on spatial analysis. So to start, I'm gonna go with notions of cartography. This is important because spatial analysis depends and relies on cartography and knowledge on maps, knowledge on geodesic information, and how to build on those notions and this knowledge to create a map that is not lying to us. Because it's very easy to have maps lying to us. So the idea is that we're going to have these notions of cartography to start building our concept of what spatial analysis is. And then we're going to go to the softwares and the files. So let's get started. So what is cartography? This is uh, the main idea here. So how should we understand cartography? It is a discipline that deals with the conception, production, dissemination, and study of maps. But more than that, it's not just creating the maps, because that anyone can do. I can draw a map right now, or even like a child can draw a map. Does it mean it is a cartography? Not so sure, because cartography seeks accuracy in representing the Earth's surface. So we're going to utilize principles from geodesy, mathematics, and astronomy. So cartography relies on very different areas of knowledge to create something that is simple for us to understand, and try to summary a complex knowledge that is mapping and geography in a way. So cartography must be understood as this accurate representing of Earth's surface. And what is a map? Since we're talking about cartography wanting to do maps, wanting to create maps, map is a symbolized and scaled representation of a geographic reality. And it is designed to present information about Earth or other celestial bodies on a surface. So what we want to do in a map is to get a piece of information about the reality, the geographic reality, and put it in a flat surface. So we can see the whole picture and see where we're going, what we're doing, how we can uh, construct, or how we can build, or how we can yada yada. So this is also useful not just for Earth, but other celestial bodies. We can do that for other planets. We can do that for stars. We can do that for almost everything that uh, has a body or a surface that we can translate from a geodesic to a flat surface. And a map must be scalable and present a reduction. We cannot have a map that is not up to scale, because how can we have a map of Durham that is the same size of Durham? It's not useful, because then how we're going to look at it, how we're going to know where we're going, how we're going to, it must be scalable. So it must be on scale and must allow reduction, um, because this reduction will give us uh, like will allow us to look at it and actually create it and use it in a meaningful way. Other than that, it's not useful because why have a map that is the size of the United States? No one wants that. It's not useful at all. It must be symbolized. So all of those symbols have a meaning, and we're gonna learn all of them in the next few sessions because some of them are mandatory. We cannot have a map that does not have any symbols. They must have. And this is important because most of our work when we're doing spatial analysis in public health, uh, when it's someone that is not familiar with spatial analysis, will put just a few symbols and forget the essential or put it in a way that is not useful, or we'll have some troubles creating those symbols to represent the north or the scale or the magnetic north or even the grading system. So there's a lot of symbols that we'll learn that are essential to any map. The map also must be a generalization and abstraction. So it needs to create something that can be generalized. And it's abstraction of the mind because it's not something that we will see and instantly recognize, but it's something that we will understand because we have the knowledge from the real world. So if we're going to the Duke campus, the Duke West campus, we know that there's the Irving Road that goes along with it, and we know where it starts, we know where it ends in the Duke campus. And when I'm creating a map of Duke campus, that will be there, and we can actually see ourselves in Irving Road when we look at it in the map. So this is the abstraction we need. If a map is not creating abstraction, if we're not be able to put ourselves in that place, then it's something that is failing. Of course, it doesn't apply to when you don't know. So you're following a map to a place, a new place. So you're going blindly on it, but it gives you a sensation that you know where you're going. So that's the abstraction. And lastly, we have the projections. So creating a map, it's not something that is, there's a magical formula, so anyone can do it, but everyone does it differently. So we have standard projections to help us understand which form or which shape we're using to create those maps because they can be very different. So it's easier for us to have standard projections to help us see and visualize the space we're working. We're going to touch on that a little bit further in the presentation. But these are the fundamental characteristics of a map. So it needs to be on scale, it needs to be reducted, it needs symbolization, it needs generalization and abstraction, and it needs a good projection. And I'm going to start with the scale. And I want you to answer me which map depicts a small scale. Is it map A, a city map, or is map B a Latin America map? Which one depicts a small scale? What do you think? Okay, so
I'm not sure if you can see the chat, Nathan, but people are
yeah, I'm
posting.
seeing the chat here. Yes,
B.
it's
Or so
B.
it's like
So the small scale is the Latin America map. We tend to say, okay, so a small scale will be the place that is smaller. So the city is smaller than the continent. But in the scale, it's the other way. So whenever we have a small scale, it means that we have a further view. So continents, countries, whether we have a large scale, when it's more detailed, and we have like a city map that we can see the lakes, the parks, the name of the avenues, points in the map. So it's a large scale when we have more details, and it's a small scale we don't have that much details. So this is important because when we're going to do a map, or going to create a map, the scale will tell us what's the difference between what we see in a map and what we see in a ground distance in real life, in a real scenario. So the scale is the ratio between the dimensions of a geographic surface represented on a map and the corresponding dimensions of the same surface in the ground. So we will have like, okay, 1 centimeter in a map represents 100 centimeters on the real world. This is a scale. Of course, we represent this as a figure that it's easier for us. So here we have 0, 25, 50, 100, 150, and 200. And we measure this. So I will say that from 0 to 25, we have 2 centimeters. So 2 centimeters in the map represents 25 meters or 25 kilometers. We don't have it here, so we don't know. 25 kilometers in real world. So 2 centimeters is 25. 4 centimeters is 50. 8 centimeters, it's 100. And that allows us to understand how far we are. So we need to measure it in a proper scale. And this is one of the things that most people usually don't understand and just put it on a map and whatever. But whenever we're doing a map, we need to be sure that this scale is right because it represents everything. If it's 1 centimeter, 1 millimeter wrong, then it will create a 50 or 100 kilometers gap, 100 miles gap. I'm not going to use miles here because I'm Brazilian. I know what to do with metrics. So 100 miles is a lot to be loose in a map. We need something that is reliable. So we want as accurate as possible. So this scale must be 100% correct. And of course, we tend to do map distance in centimeters, usually not millimeters or anything higher than that. Centimeters is the standard, but the ground distance, we usually go for kilometers or depending on where you're on, miles. And we can also use as meters, we can also use as centimeters, but the most useful ones are, of course, miles and kilometers, especially when you're doing a small scale. But why is a small scale Latin America and not a city map? Because the small number is when you divide 1 centimeter to 100 kilometers and not 100 meters. So that gives us a smaller number. So that's why a small scale is a larger view and a large scale is a smaller view. So it's the other way around. Scale is one of the mandatory things we want and we need on a map. Without this, we cannot have anything because we don't understand what is happening. We don't understand how far it is because we'll think that, okay, it's close. No, it's not. We need the scale to tell us how far it is, how close it is. So scale is the first one. and it's important and it's kind of easy. We learned this in primary school, I think. So it's something that we do on geography classes, if you have geography classes. Um, and yeah, it's something that creates a sort of understanding. How can I say this? We tend to confuse a lot. So a small scale, larger view, large scale, small view. And then we have this. Every map lies. All the map lies because of the projection. So every map must have a projection, is one of the mandatory characteristics. And this map projection is a mathematical and proportional transformation of Earth's sphere network of latitudes and longitudes into a flat plane surface, meaning that I have a giant spherical form, shape, and I'm gonna do a translation from a sphere to a plane surface, a flat surface. That is kind of tricky. So because of this, because of the Earth being spherical and a map being flat, is impossible to represent any large portion of the globe without some degree of shrinking, stretching, or breaking. So every map will lie to you. You will need to choose which lie you want to tell. We're going to see this in the next few slides. So the true shape of Earth and the mathematical model. The true shape of Earth is the geoid, so it's irregular. It is defined as the equipotential surface of gravity at mean sea level. So we use the true shape of Earth when we want altitudes. When we want to represent on a map the relevo. How can I say this in English?
Relief?
Yeah, like
Is it relief?
relief is.
Yeah.
Relief. Okay. So we want to represent relief because that is where the geoid applies. But for maps, that's not something that very useful. How we're going to represent this irregular shape? We cannot. So we create a ellipsoid of revolution that is a perfect geometric volume. So you can see here that there's like a shadow that is irregular. That's the real Earth shape. And we create this stronger, bolder shape of Earth that is called the ellipsoid of revolution that is round, completely round. And it allows us to create and calculate those geographic and there's cartographic formulas. So we can use this for coordinates, latitude and longitude. So this is the basic of GPS. We need to create something that is perfect geometrically because the Earth is not. It is a rock floating in the space. So it needs to be perfectly for us to be able to calculate what we need. So this will be important because we can create any type of projections based on this ellipsoid of revolution. And we can start at any point. But if you start at any point, you need to create all the other points based on this first point. So the mathematical mode, this perfect geometrical shape that we use, it's not the same for everyone. And this is, we need to be careful because sometimes we're going to use a file that is based on the US standard shape. And I'm going to use the software that I use automatically transforms to the Brazilian standard. And then all the things get distorted. stretch it, shrink it, because it's a different kind of cartographic calculation. So this is where we must be more careful, because this will get you different results than we expect. So the most important projections are characterized by their geometric properties and what we want to use them for. The most famous ones are the cylindrical projections. We have the Mercator, Peters, and Lambert. We also have conical projections, simple conical to standard parallels, and we have the azimuthal projection, the gnomonic, stereographic, and orthographic. I have it here, what all of those means. So we have the cylindrical, the conic, and the azimuthal. And we have the point of tangency. The only place a map does not lie is where the paper touches the sphere. So you can see here, it's in white. So it's closer to the equator here and here. Here we also go a little bit more to the, in this particular drawing, the north hemisphere. So where the paper touches the sphere is where the map will not lie to you or to us. So the farther we have from this point of tangency, the greater the distortion. So the cylindrical projection wraps around the equator, and it's ideal for world maps and global navigation. It's the easier one. The conic projection will be those mid-latitudes, so will be like around here or around here, depending on where you're representing. And then we have the azimuthal or planar projection that is ideal for polar mapping, aeronautics, and calculating radial routes from the center. Because this will create like sections, this azimuthal will create sections of horizons, lines of horizons. We won't go deeper into that because it's not necessary. Is there a global standard contrast to the example Brazilian or US? Yes, there is a global standard. We're going to touch on that a little bit further in the presentation. I'm going to talk about this in the next slide, I think. Don't worry. So from all of those, the cylindrical is the most useful ones because it will give us an easier way to work with them, because the paper, the cylindrical projection, will give us a touching point that is easier for us to understand. So it wraps around the equator, and we can just, it's easier for us to even visualize how we can wrap a ball. We usually start with creating a cylindrical form, a cylindrical shape, and then we're gonna go like a candy. So if a candy, we take it off the paper, it will be paper that starts cylindrically, and then we, how can I say this?
Twist it.
Twist it, yes, exactly. So if we untwist, it will be like a cylindrical. So it's the easiest form for us even to visualize in our minds. So the abstraction here is easier in cylindrical. So here I want to show you the difference between Mercator and Peters. We've probably seen the Mercator a lot, so it's the standard for almost every map. But there is a problem with the Mercator. It creates bigger countries or bigger lands as it goes far or further from the equator. So the equator is here. As we go up, we can see those boxes, all those squares, slowly turn into rectangles because it's getting distorted. So Greenland, for example, it's not that big because here it's like the same size of Africa and it's way smaller. It's not even like comparable. The same goes for Russia. Russia seems too big, and it's not. United States, China, all of those, we see this as huge countries, or even Antarctica. Antarctica is huge. No, it's not. It's not that big. We don't have that much.
It is too pretty big, but I mean not that big.
That's what she meant.
It is not. It is not. I mean, if we're counting like from a smaller perspective, I mean, it's big for me to walk it all alone, but it's not that big that we cannot see it all in a map or just go from one border to the other. It's feasible. It's very feasible. So it's not that big. Peters, on the other hand, will maintain shape. It will maintain this size volumetrically. But as you can see, it will stretch a little bit. So it's not that centered. It's more towards the pole than what Mercator did, that is more towards the center, the equator. So the pink here, it's the actual sizes. So you can see that Africa, it's way bigger here than it is in the Mercator. The same goes for Brazil or South America in general. And why am I saying that uh, Antarctica is not that big? Because you can see here that South America goes up here and it's very close. And it's almost the same size of Asia, probably, or even a little bit smaller. So it is big, but it's not that big. So as we understand these projections, we need to understand how to transform that into something feasible for us to use in a software. Are we going to use Mercator? Are we going to use Peters? Are we going to use a conical projection? There are standards. We usually go for Mercator because it's the most recognizable one, but we can also use other ones. And for that, we must choose a datum or datum that is a reference for the ellipsoid. So this is a projection. So do you all remember that ellipsoid of revolution? This is where we choose which form, which shape we're gonna use in our mapping. So it represents the Earth is slightly flattened sphere. So we'll have not a geoid, but more like a perfect circle or spherical form, spherical shape. It's where we have the contact to the terrain. Also, where this projection, where this fuzzy sphere will touch the actual geoid form, geoid sphere. So we have some standard datums. Globally, we'll go for WGS 84. For USA, we have NID 83, and for Brazil, we have Sirgas 2000. Those are all just codes for these datums. They don't represent anything other than that. Okay, so these are codes that we need to know because whenever you're using a global datum, but you're actually modeling a USA uh, analysis that is strictly to the USA, you're going to prefer NAD 83 because it's easier for us to model using the appropriate datums. So globally, we have this for USA, for Brazil. I look it up for Tanzania. The ones they're using now is WGS84. But there's a lot of different atoms that we can use. So if you search for a list of the atoms, it will be around 200 probably, and like the basics, because there's a lot, really a lot. And we have different like Sirgas. So this Sirgas 2000, we have Sirgas 2000A, Sirgas 2000B, Sirgas 2000C, there's a lot. Sometimes we have just the standard, sometimes we have more. We'll touch that in a little bit. Yes, Ashley?
Sorry if I missed it that you said, but how would we know, other than by asking Natan, the expert, which datum should we use depending on which geography we're messing with?
Okay, so do not ask me. First of all, no, you can ask me. That's okay. Whenever you're using a software that works with spatial data, so geographic information systems, GIS, it will tell you which one you're using. And then if you want to reproject, this reprojection allows you to change these datums. How we can know which one to use usually comes from experience, but also you will want to check on statistical bureau of your country to see if they say anything like, oh, we use this as the standard, we use that as the standard, so you will know. Of course, you won't get wrong with WGS84 because it's globally used. But if you're doing Brazil, it's common knowledge for anyone that is working with spatial analysis that is Sirgas, because the file, the data file, will be already projected in Sirgas. So the standard is the one that you downloaded in, and then you change it if you want. So if you want to download a shape file from the United States Statistical Bureau, it will probably come in NAD 83. So you choose by seeing which country you want to work with, and you can just Google it to see which is the most commonly used datums for that. But if you don't know, or there's an inconclusive answer, WGS84. That's going to be the most useful ones. So I see here that Edwin is asking, why is there a variation from the global datum? Let me show you. So here we have two datums that are trying to pinpoint here the same spot on Earth, but I'm starting it a little bit closer to the left in the purple and a little bit closer to the right in the green one. So the starting point is different. So why do we use different ones for Brazil, United States, Tanzania? Because we want to start closer to the country that we're working. So imagine that you're wrapping a candy. You need to know which part of the shape of the candy to start wrapping. In the global shape, or in the global scenario, you will choose to start in the country that you will work with. So if I'm Brazil and I want to work with Brazil, I will start wrapping the candy where Brazil is. So it touches it better, because if it touches it better, the map will be better. It will lie less, because we're trying to create a flat thing, a flat surface from a geoid surface. So the difference is where we start the wrapping, or we start the cylindrical projection. So we want that to be closer to the country that we're working with. Oh, so I'm doing the whole world. Then you're gonna use the global. But it's easier for me to do a spatial analysis in Brazil if the datum is touching Brazil. That will be more useful, more accurate. So datums work that way. It will be easier for us to start at this country. Is it a little more clear now?
Yes, Nathan. Yes, makes sense.
Okay,
And
perfect.
the kanji analogy, very relatable. Brilliant.
Yeah. So I
Nathan,
love
can
to
I
use this.
can I add something as well?
Of course.
Yeah, so one thing maybe to think about is that you don't, although this is confusing, it is really workable. So you can always change those projections and the datum that you're going to use for your type of analysis. The big thing is you want to make sure that all of your data is in the same projection whenever you're doing your analysis. Otherwise, you're going to run into problems. But also, then after your analysis is done, your project is done, you can always check if the journal you're going to submit to has some requirement, if your government has the recommendation for you to use, so you then adapt at the end. Those are things that you don't need to decide up front. You can always
Yes.
go back and fix.
And one thing is important, it must always go in the map. So when you're doing a map and you're going to use in a paper, in somewhere in the map must be specified which datum you used, because map lies. So we want to know which lie I'm believing. So we must specify the datum. Thank you, Geometer. That was really useful. So as we understand datum, where we touch the sphere, we go to CRS, the Coordinate Reference System. So now we're going to go to actually identifying locations. So those coordinates that we use to really understand where that point is on the map or is in the surface. So these coordinates reference systems, CRS, are used to precisely identify location on the Earth's surface by associating spatial data with a specific coordinate system. So we have a lot of different CRS. The most common ones are the geographic and the projected. So I have here drawings of how we can understand the CRS. So we have the Cartesian coordinate system. We have 3 axes, so x-axis, y-axis, and z-axis. And it's a Cartesian, so it's based on the Cartesian model. We have the geographic, which puts the angles to create the longitude and the latitude. And we have the projected, which is not on the sphere, is a plane, a flat surface that we put in a Cartesian model to create an x and y axis, and then we pinpoint. It will be easier if we go here and start with the geographic. So for geographical, I like to always start thinking of latitudes than longitudes. because latitudes, it starts at the equator and they always flat. So think of an orange, and instead of starting from the top, you start from the middle, and you're gonna slice it parallelly from the middle. So you start here, and then you're gonna here, and then here, and then here, and then here. So latitude, it starts at the equator and goes in parallels up north and down south. So it starts at 0 degrees, and then it goes up 90 degrees to north, or go down 90 degrees to the south. Whenever it's going north, it's a positive number. Whenever it's going down, it's a negative number. Why is that? So we can understand if it's north or if it's south. The north hemisphere and the south hemisphere. So if we're going to the pole, the magnetic center of the world, to the North Pole, it will be closer to this magnetic, so it's positive. And if we're going down, we're going further away from the magnetic pole, it's negative. All starting at the equator. So equator is 0, and then we're gonna go from 0 to 90, up and down. So this is latitude. Latitude is always flat. Longitude, on the other way, converges at the North Pole. So it's not parallel. It goes from bottom up, from bottom down and bottom up. I'm not sure how top up. From top to bottom. Let's check with that. It's easier. So from top to down. And this is a semicircle. So it goes from 0 to 180. So longitude converges at the top and converges at the bottom. We created the 0 at Greenwich because we wanted. It's a strong pronoun to use. That was the European colonization, but we allow them to use this as the standard. So Greenwich is the standard as 0, and you go all the way to 180. So this will give us east and west. East, so right, is a positive number. West, left, is a negative number. So latitude and longitude will converge together to create the pinpoint. Like Shanghai is latitude 31.2 degrees north and longitude 121.5 degrees east. So this is the coordinate. So geographic uses this. So you see that I'm using here the angles, just like I showed here. So I'm using the angles of where it is. I'm not using like a paper. I'm using the actual point and the angles in a sphere. And this sphere, of course, is our datum. The same goes for Rome. So it's 41.5 degrees north, 12.5 degrees east. See, there's no negative numbers because we're not in south or in west. And of course, that if we're putting N, E, we can put as W, and then we won't put the negative here, but it's useful to use the negative numbers to demonstrate where it is. Most softwares, most GIS softwares will give you the numbers in positive or negative values. So this is geographic. It's one of the most used alongside with the UTM. So the UTM is a little bit more complicated than the geographic because we want to create a flat surface. So instead of using the angles, I'm taking a part of the sphere, flatten it, and then pinpointing it in a Cartesian model with X and Y. So here I have my sphere and the paper that wraps it. And the paper that wraps it is touching perfectly here. So for the UTM, the Earth is divided into 66 degrees zones. What? I don't understand the Greenwich. Oh, okay. I got it. Sorry.
No worries.
So I'm just typing here. So it's 6 zones of 6 degrees each. So when we're using UTM, we have the surface of the Earth divided into 60 zones of 60 degrees each because it's 360 degrees, the whole sphere. And the 60 zones have a meridian that divides each zone into 3 degrees zones. So we have, like you can see here in this image, that we have a zone or a time zone. That's what we use for time zones. That is divided by a meridian here that divides these 6 degree zones into 2 3-degree zones perfectly. Why is this useful? Because then it's a flat surface. And in a flat surface, I can just put an X and a Y axis and then put it in a cartographic or a Cartesian model. So in this model, which is the most used, the x-axis is in projection with the equator, and the y-axis coincides with the projection of the central meridian of the zone and points towards the north. So it always goes up the north. And the central meridian is whenever meridian is in that specific zone. So the time zones we have, like here in Brazil, is GMT -3, while in Duran is GMT -4, now that we have daylight saving. And it's minus because it's minus to the Greenwich. But the projections of UTM starts at 1 in the far west and goes all the way to the far east up to 60. This will be important in our more practical class. Any questions? I know it's a lot of information and it's not the most easy information for someone that is in public health or any type of clinical work to understand about cartography all of a sudden. I can explain again about the UTMs. So think of a paper model of the Earth, like a sphere. This paper model, you want it to be flat. how will you cut it?
Mm-hmm.
You cannot cut it in a square shape because you're gonna lose ground.
Mm-hmm.
So how's the best way to do it? So whenever you're cutting like an onion from the top, you go this and this and this and this. You create like, or you can even an orange.
Mhm.
So it's those semicircles. This is what UTM does. It divides not into a square, but into pieces that can be flattened, and this flattened can be transferred into more approximately to a square. It doesn't need to be a square, of course, but it's something like this. Let me draw. So you have this sphere here, and I'm not good at drawings. You're not gonna be able to cut it into a rectangle or a square because you're gonna end up losing this and this. So what we do, we divide it like we're dividing a orange. I'm not good at drawings, guys. So if we're dividing this way and we take out this piece, it will be like this. And of course, if we zoom in this piece, it will be a square or a rectangle in this case because I'm drawing a
But it's flat,
rectangle,
flat
but it's
thing.
flat. And then if it's flat, I have a y-axis and an x-axis, and I can just pinpoint it here.
Yeah.
And
I think
then
it's sorry.
it will be a direct coordinate from the surface, but projected in a square or in a rectangle. Go ahead, Ashley.
To me, it's like a helpful way to think about this is like if you had to print on paper a globe and make it, the pictures that you have on the bottom right is like what you would print on paper to fold it perfectly in a sphere without covering up any places, right?
Yeah.
Because like if you did make it a square, you would have to fold and crumble places that
Yes,
not showing.
exactly. So UTM, it's a projected because we're projecting it on a flat surface when Earth is not actual flat. So that's what UTM does. That's why we have an X and a Y axis. It's easier for us to project this. I will know exactly to where it is, but I will also be a little bit off from the geographic because it will be a little off from the geographic because I'm not using the angles, I'm using the flat surface.
Okay, and then the 6 degrees and the 3 degrees will be the middle point of the
The 3 degree will be the middle point. So here we have the central meridian, and then we have here 3 degrees, and here 3 degrees, from here to here.
Okay.
And these 3 degrees, we can take any part of it and create this flat surface. That's
Yeah,
what
cool.
UTM does.
Makes sense.
Okay. I guess that was it for today. Any other questions?
Do you want to tell us what we'll look at next week?
Next week, we will download the first software, GIS software, and then we're going to start looking at those cartography notions into what it means in those softwares and how we can reproject and start mapping effectively. So yeah, we're gonna download it together and then start creating maps the next section.